Hello. Candace just showed you several examples of solving quadratic equations using the zero principle. In a few of her examples, she had to do a little bit of work before she was able to use the zero product principle. In several of my examples, I'm going to have to do a whole lot of work before I can use the zero product principle. That's why I've chosen to call this portion of the lesson Enabling the Zero Product Principle. So what do we need to do to enable the zero product principle? Well, let's start with this example. Suppose we were asked to solve x times x plus 5 equals 14. If I was teaching this class in a classroom full of students, I'm pretty sure that somebody would ask me, hey, can we say that x equals 0 or x plus 5 equals 0? To which I would respond, well, sure, we could say that, but the question is, would that lead to a solution to our equation? Well, let's remember something. And that's that there's a reason it's called the zero product principle. Because if either x is 0 or x plus 5 equals 0, what's the product going to be? Well, if x is 0, then x times x plus 5 is 0 times x plus 5. Notice in the second factor, I didn't bother to replace x with 0 because it doesn't matter what number I get for the second factor. 0 times the second factor is going to be 0. It's a zero product. Likewise, if the x plus 5 factor is 0, then x times x plus 5 is going to be whatever number x is times 0, which is 0. It's the zero product principle. So letting x equal 0 or x plus 5 equals 0 is not going to give us a product of 14. So sometimes people will say, well, then can we say that x is 14 or x plus 5 is 14? Well, let's remember, there's a reason there isn't anything called the 14 product principle. There's actually a couple reasons there's nothing called the 14 product principle. The first thing is this. If the product is 14, does one of the factors of the product have to be 14? Well, no. There's all sorts of pairs of numbers you could multiply together and get 14. What's an easy example? 2 and 7, and neither factor is 14. There's the flip side of this as well. If one number in the product is 14, does that mean that the product has to be 14? No, only if the other factor just happens to be 1. Look at our two factors, x and x plus 5. If x is 14, what's the other factor? It's 14 plus 5, which is 19. And 14 times 19 isn't 14. How about if x plus 5 is 14? Is the other factor 1? No. And if the other factor isn't 1, then 14 times the other factor, again, isn't 14. Remember, there's a reason there isn't anything called the 14 product principle, and there's a reason there is something called the zero product principle. And that's that if you have the product of two numbers and the product is 0, you do know that one of the two numbers in the product has to be 0. So it seems to me that we need a product of 0. And in order for us to have a product of 0, I think we better come up with a strategy. So here's our strategy. We're going to begin by expanding each side of the equation. We're then going to use the addition property of equality so that one side of the equation is 0. Remember, we want a product of 0. Then we want to factor the non-zero side of the equation. We want to apply the zero product principle, and then we want to check and state our solutions. And we need to remember to check our solutions in the original equation. Let's do this several times. In this particular example, I'm starting with the equation x times x plus 5 equals 14. The first step in our strategy was to expand both sides of the equation. The left side of this equation expands into x squared plus 5x. The right side of this equation is already completely simplified. Now we need one side of the equation to be 0. When I decide which side of the equation I want to be 0, I think about the fact that I'm ultimately going to have to factor the non-zero side, and factoring, for me anyway, and I suspect for you as well, is a whole lot easier if you have a positive coefficient on the squared term. I want x squared to have a positive coefficient, so I'm going to move all my terms to the left by subtracting 14 from both sides of the equation. That gives me x squared plus 5x minus 14 equals 0. Does x squared plus 5x minus 14 factor? You betcha. it factors into x plus 7 times x minus 2. Check it out. I have a zero product, so I can use the zero product principle, which says that one of the two factors in this expression needs to evaluate to 0. That is, x plus 7 needs to be 0, or x minus 2 needs to be 0. Solving the first linear equation, x is negative 7, and solving the second linear equation, x is 2. So it looks like the solutions to my original equation are negative 7 and 2. We need to check. If x equals 2, then x times x plus 5, I'm going to do a little bit of the arithmetic in my head. X is 2, no arithmetic there. The little bit of the arithmetic that I'm going to do in my head is the x plus 5 factor. If x is 2, 2 plus 5 is 7. So x times x plus 5 is 2 times 7, which is 14. I'm not going to just check. I am going to look back and say, you know what, that is what I wanted, x times x plus 5 to equal 14. How about if x is negative 7? If x is negative 7, then x times x plus 5 is negative 7 times, what's negative 7 plus 5? That's negative 2. And the product of negative 7 and negative 2 is 14. Both of my solutions check. I need to state a conclusion. The solutions are 2 and negative 7. How about 42 equals x squared minus x? First thing I need is 0 on one side of the equal sign. This time, I'm going to make the left side of the equal sign 0. Again, my motivation being, I want a positive coefficient on my squared term because it makes factoring a whole lot easier. So first thing I'm going to do is subtract 42 from both sides of this equation. And that gives me 0 equals x squared minus x minus 42. You know, in our strategy, the first step was to completely expand both sides of the equation. I kind of skipped by that step because there wasn't anything to expand. All right, now we have one side of our equation 0. We need to factor the non-zero side of our equation. How does x squared minus x minus 42 factor? It factors into x minus 7 times x plus 6. How did I come up with that? I was looking for two numbers that multiplied to negative 42 and add to negative 1. And those two numbers were negative 7 and positive 6. Now that I have a product that equals 0, I can use the zero product principle. And the zero product principle says that one of those two factors has to equal 0. So from my first linear equation, x has got to be 7. And from my second linear equation, x has got to be negative 6. So it looks like my solutions are going to be 7 and negative 6. But what do I need to do? I need to check, and I need to check in the original equation. So let's check what happens when x is 7. The variable side of my equation, which is x squared minus x, becomes 7 squared minus 7, which is 49 minus 7, which is 42. Now, I'm not going to just put a little check there. I am going to go and make sure that that's what I wanted the variable side to equal, and it is. I want the variable side to equal 42. Now, I can put a little check there. How about if x is negative 6? If x is negative 6, then x squared minus x is the square of negative 6 minus negative 6. Do you see something I wrote down wrong? I hope so. When you square a negative number, you need to put the negative number in parentheses. Otherwise, the squared only affects the base of 6, and the result would be negative 36, not positive 36. But since we are squaring negative 6, the result is going to be positive 36. Subtracting negative 6 is the same as adding 6, and woohoo, we do get 42. This answer checks as well. All we need to do is state our conclusion. The solutions are 7 and negative 6. How about y times 21y minus 32 equals 5? Sometimes, especially when taking tests, students get a little freaky-deaky and they start making up rules like the 5 product rule. And they say y has to equal 5 or 21y minus 32 has to equal 5. Well, let's review. If one of the factors is 5, does that mean the product has to be 5? Heck no. The only way the product would be 5 is if the other factor just happened to be 1. The only number that we have this product principle is the number 0. If the product of two numbers is 0, one of the two numbers in the product has to equal 0. So what's the first step in our strategy so that we do have a product of 0? We need to expand both sides of the equation. So we've got y times 21y minus 32 equals 5. Distributing y through the parentheses on the left, we have 21y squared minus 32y. That still equals 5. Since I want y squared to have a positive coefficient, I'm going to make the right side of the equation 0, which I can do by subtracting 5 from both sides of the equation. So now we have 21y squared minus 32y minus 5 equals 0. I want to use the 0 product principle, so I need a product on the left side of the equation. Let's go ahead and factor the left side of the equation. I got to tell you, even I do not see how the left side of the equation factors. I think I'm going to use factoring by grouping. Now, looking at the coefficient on the squared term and the constant, they multiply to negative 105. So what I'm looking for is two integers that multiply to negative 105 and add to negative 32. Well, I don't know about you, but right offhand, I can't think of numbers that multiply to negative 105. So what I do in this situation is I think about prime factorizations. What's the prime factorization of 105? Well, I know 5 goes into 105, and specifically 5 goes into 105 21 times. 21 in turn factors into 3 times 7. So the prime factorization of 105 is 5 times 3 times 7. So let's start looking for pairs of numbers that multiply to negative 105, and we're trying to find the one that adds to negative 32. Well, let's look at 1 and negative 105. I don't really know what that adds to, which is a little bit of a lie, but I do know it doesn't add to negative 32. Let's go up to 3. What would we have to multiply 3 by to get negative 105? Well, looking at my prime factorization, I'm missing the 5 and the 7, which multiplies to 35, so I'd need to multiply 3 by negative 35. And yippee-yi-yay, that adds to negative 32. So let's go ahead and take our minus 32y term and break it up into 3y minus 35y. In my first two terms, there's common factors of 3 and y. And when I factor those out, I'm left with 7y plus 1. Can I factor something from my second two terms that also leave behind 7y plus 1? Sure, negative 5. Negative 5 times 7y is negative 35y. Negative 5 times 1 is negative 5. So this all still equals 0. I can't use my 0 product principle yet because the primary operation on the left at the moment is subtraction. That's the last thing that's happening in order of operation. So what I need to do is I need to go ahead and pull out my common factor of 7y plus 1. That leaves behind 3y minus 5. This product has to equal 0. In order for this product to equal 0, one of those two factors in the product has to equal 0. So it has to be the case that 7y plus 1 equals 0, or 3y minus 5 equals 0. Well, if 7y plus 1 equals 0, 7y equals negative 1, which means y has got to equal negative 1/7. If 3y minus 5 equals 0, 3y equals 5, so y has got to equal 5/3. So my proposed solutions are negative 1/7 and 5/3. But you know what I need to do with those. I need to check my proposed solutions. So let's do some checking. If y is 5/3, then the variable expression y times 21y minus 32 is 5/3 times 21 times 5/3 thirds minus 32. Now, I could go ahead and multiply 21 and 5 and then divide by 3, but I'm going to make the observation that 3 goes into 21 7 times. So 21 times 5 thirds is the same as 7 times 5, which is 35. 35 minus 32 is 3. 3 from my 5 thirds in the denominator divides into 3 in the numerator, and all I'm left with is a factor of 5, and that is what I wanted y times 21y minus 32 to equal. So 5 thirds checks. How about negative 1/7? Well, if y equals negative 1/7, then y times 21y minus 32 is negative 1/7 times 21 times negative 1/7 minus 32. 7 goes into 21 3 times. So 21 times negative 1/7 is negative 3. Negative 3 minus 32 is negative 35. 7 goes into 35 5 times. Since I'm multiplying together two negative numbers, the result is positive. So this product is 5. So my solution of negative 1/7 also checks. So the solutions to the equation are 5 thirds and negative 1/7. Let's look at 64x squared equals 49. What's the first step in our strategy? Expand both sides. What's the second step? Make one side 0. I'm going to make the right side 0, so my x squared term has a positive coefficient. Let's factor the non-zero side. The non-zero side is a difference of squares. 64x squared minus 49 factors into 8x plus 7 times 8x minus 7. Because of the zero product principle, either 8x plus 7 equals 0 or 8x minus 7 equals 0. I'm going to go ahead and solve these in my head. If 8x plus 7 equals 0, x equals negative 7/8. And if 8x minus 7 equals 0, x equals 7/8. What's the missing step? In the first equation, I subtracted 7 from both sides of the equation. In the second equation, I added 7 to both sides of the equation. I'm going to encourage you to experiment and see if you can do that step in your head just to save yourself a little bit of time. Sometimes when we have numbers that are solutions that are opposite, we just write a little compact symbol that says x is plus or minus the opposite numbers, which are plus 7/8 and minus 7/8. Hey, let's check. Let's check plus or minus 7/8. Well, I'm making an observation. The only thing that's happening to x in this equation is that it's being squared. And it doesn't matter whether I square positive 7/8 or negative 7/8. In both cases, I get positive 49/64. So I can do two checks in one. If x is either positive 7/8 or negative 7/8, 64x squared is just 64 times 49 over 64, and guess what that is? That's 49, which is what we want, so the solutions are plus and minus 7/8. How about 5t squared equals 10t? This is a pretty small-looking equation. I would actually, unfortunately, anticipate a lot of incorrect answers if this equation showed up on a test. I'll talk about that after I solve it. What's the first step? Expand both sides. Nothing to expand. What's the second step? To make one side of the equation 0. I'm going to make the right side of the equation 0 so that I have a positive coefficient on t squared. Now that I have 0 on one side of the equation, I want to factor the non-zero side of the equation so that I can use the zero product principle. I see common factors of 5 and t in both of the terms on the left. When I factor out 5t from the left, I leave behind t minus 2. So 5t times t minus 2 has to equal 0. One of the factors on the left has to equal 0. guess what? 5 don't equal 0. So it's not 5 that equals 0. It's either t that equals 0 or t minus 2 that equals 0. What's the solution to t equals 0? Well, that's 0. What's the solution to t minus 2 equals 0? Well, that's 2. So it looks like my solutions are going to be 0 and 2. Before I check, I want to mention the mistake that I'll frequently see people make. They'll look at this equation, 5t squared equals 10t, and they'll say, you know what? Both sides of the equation can be divided by t. And they'll go ahead and they'll divide t from both sides of the equation, leaving 5t equals 10. Well, the equation 5t equals 10 only has one solution. When we divided both sides of the equation, we threw away the solution t equals 0. How did that happen? It happened because we did something illegal. If t is 0, you can't divide both sides of the equation by t. So you need to make sure that you keep your focus, that you want to factor. You don't want to divide when variables are involved. Let's go ahead and check 0 and 2 in our original equation. If t is 0, then 5t squared is 5 times 0 squared, which is 0, and 10t is 10 times 0, which is 0. So the two expressions do have the same value when t is 0. How about when t is 2? If t is 2, then 5t squared is 5 times 2 squared, which is 5 times 4, which is 20, and 10t is 10 times 2, which is also 20. The two expressions are equal when t is 2. Consequently, the solutions are 0 and 2. How about x times x plus 8 equals negative 16? First thing I need to do is distribute on the left side. X squared plus 8x equals negative 16. Now I need one side of the equation to be 0. I can do that by adding 16 to both sides of the equation. I can either recognize the left side now as a perfect squared trinomial, or I can think, what two positive integers multiply to 16 and add to 8? In either case, I see that the left side factors into x plus 4 times x plus 4, or I could have written x plus 4 quantity squared. No matter how you look at it, using the zero product principle, what has to be true? X plus 4 has to equal 0, or x plus 4 has to equal 0, or if you're thinking about what number do you square that gives you 0, well, that would be 0, or x plus 4 has to equal 0. Face it, x plus 4 equals 0, so x has got to equal negative 4. Well, hold on a second. That's only one solution, negative 4. What's up with that? Well, it turns out that quadratic equations can have only one solution. We've seen several examples of quadratic equations that have two solutions. So quadratic equations can have one solution or two solutions. Quadratic equations can also have no solutions, at least over the real number system. If you keep taking more and more math, you'll see that there's other types of numbers. And once you get into these other types of numbers called complex numbers, it turns out that quadratic equations always have either one or two solutions. But over the real numbers, they also can have no solutions. We still need to check negative 4 in our original equation. So if x equals negative 4, then x times x plus 8 equals negative 4 times positive 4, which is negative 16, which is what we wanted x times x plus 8 to equal. So it is true that the solution is negative 4. Holy moly! 2t squared plus 10t plus 8 equals 3t minus 2 times t plus 4 plus 16. That took my breath away when that one came up on the screen. Sometimes people really start freaking out when they see so many variables. If that happens, pause. Take a breath and compartmentalize the problem. Remember, we have a strategy. So all we need to worry about right now is the first step in our strategy. And the first step in our strategy is to expand the expressions on either side of the equal sign. So that's all I'm focusing on right now. I'm not worrying about way down the line, what is my solution? All I'm thinking about right now is expand. You know, expand, that's kind of a nice, peaceful thing to do. On the left, there's nothing to expand. So it was pretty easy to expand the left. How about on the right? I need to do some foiling. 3t times t is 3t squared. I like to OI in my head because when two terms add, combine, like terms, it's usually the OI terms that do it. So my O is 3t times 4, which is 12t. My I is minus 2t. 12t minus 2t, that's plus 10t. My last multiplied a negative 8, and I still have my plus 16. I think I'm going to be less likely to make an error if I go ahead and combine my like terms on the right before I start moving terms around. So let's rewrite this as 2t squared plus 10t plus 8 equals 3t squared plus 10t plus 8. Now I want one side of the equation to be 0. This time, I'm going to make the left side of the equation 0. Why am I doing that? Because I want t squared to have a positive coefficient. It's going to make factoring easier. And if I subtract 2t squared from both sides of the equation, I will have positive 1t squared on the right. So I have positive 1t squared on the right. When I subtract 10t from both sides of the equation, 10t, it's out of there. What happens when I subtract 8 from both sides of the equation? It's out of there as well. Holy moly, all I'm left with is t squared on the right side of the equal sign and 0 on the left side of the equal sign. Gee whiz, this big complicated equation turned out to be equivalent to the weeniest of all equations, t squared equals 0. What number can I square that gives me 0? There's only one, and that's 0, because if you get a product of 0, one of the numbers has to be 0, so if you're squaring and getting 0, the number you're squaring is 0. Say that 10 times. T is 0. But we need to check in our original equation. If t is 0, then 2t squared plus 10t plus 8, I'm just going to check this in my head. If t is 0, 2 times t squared is 0. 10 times t is 0. What am I left with? I'm left with 8. How about 3t minus 2 times t plus 4? Well, 3t is 0. And if you subtract 2, you get negative 2. What's t plus 4? Well, t is 0. So this is 4. We're adding 16. Negative 8 plus 16 is 8. Check it out. When t is 0, the expressions on either side of the equality sign in my original equation evaluate to the same number, that being 8. So it is true that 0 is indeed the solution to the equation. Oh boy, here's another scary looking equation. You know what? I've been in your shoes. I know what it's like to be in a testing situation and encounter an equation that kind of makes the adrenaline start going because maybe you're getting a little bit panicked. And I know a really common error that I have seen students make on this particular equation. They look at it and they kind of start panicking and they say, you know what? 2t minus 2t is 0, and 0 times t plus 2 is 0, so my life would be a whole lot easier if I rewrote the right side of this equation as 0 times t plus 2. Well, your life would be a whole lot easier, that's true, but only in the short term, because in the long term, you'd have the wrong answer to the question, and when you got your test back, you'd be thinking, you know what, my life wasn't so easy after all. What's the mistake? The mistake is rooted in order of operation. We don't do the subtraction on the right first. We do the multiplication on the right first. Those two t's don't subtract to 0. So we need to go back to our strategy. And we need to focus on one step at a time. And the first step in our strategy is to expand both sides of the equation. Distributing on the left, we get t squared plus 4t. Order of operations says that that multiplication happens before the subtraction. So on the right, we have 2t. Distributing minus 2t through the binomial, we have minus 2t squared minus 4t. Let's combine like terms before we start moving things back and forth. t squared plus 4t equals negative 2t squared minus 2t. Since I like my squared term to have a positive coefficient, I'm going to make the right side of the equation 0. Adding 2t squared to both sides of the equation, I have 3t squared on the left. Adding 2t to both sides of the equation, I have plus 6t on the left. This equals 0. I want to use the zero product principle. I need a product. How do I get a product? I factor. So let's factor the left side of the equation. Both terms have common factors of 3 and t. That leaves behind t plus 2. This product equals 0. Since the product is 0, the zero product principle tells me that either 3 equals 0, ain't going to happen, or t equals 0, or t plus 2 equals 0. So it looks like my solutions are 0 and negative 2. But I bet you know what's coming next. We need to check 0 and negative 2 in our original equation. If t is 0, then t times t plus 4 is 0 times 4, which is 0. Let's see what we get on the right side of the equation when t is 0. When t is 0, the right side of the equation is 2t plus 2t times t plus 2. So that's going to be 2 times 0 plus 2 times 0 times 2. I'm seeing a whole lot of times 0 in there. Anytime I got times 0, it's 0. So we've got 0 plus 0, which is 0. Both sides of the equation are 0 when t is 0, so 0 is a solution to the equation. How about when t is negative 2? If t is negative 2, then t times t plus 4 is negative 2 times positive 2, which is negative 4. What's the right side of the equation? The right side of the equation is 2t plus 2t times t plus 2. When t is negative 2, that evaluates to 2 times negative 2 plus 2 times negative 2 times 0. That would be negative 4 plus 0, which is negative 4. Both sides of the equation evaluate to negative 4 when t is negative 2. So negative 2 is a solution as well. So it looks to me like the solutions are 0 and negative 2. And that's it for me. And Ann is going to come beguile you with some application problems that involve the zero product principle.
So in this last part of the lesson, we're going to look at some applications involving quadratic equations. Here's our first problem. We're given a formula, and this formula will give us the sum of the first n natural numbers. So what the heck does this mean? Well, let's take the first 7 natural numbers. We want to confirm the formula for n equals 7. Now, what we need to do to confirm the formula is basically just add up the natural numbers from 1 to 7, and then we'll use the formula. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Let's see what that equals. 1 plus 2, that's 3, 6, 10, 15, 21, 28. So the sum of 1 through 7 natural numbers, that's 28. Let's use the formula. If n equals 7, then the sum, s, equals 1/2 times 7 plus 1, that's 8. 1/2 of 8 is 4. 4 times 7 is 28. We've confirmed the formula. Now, as I was writing out 1 through 7 and adding them up, you can see why it's probably nice to have a formula to do this. Now we're going to work with this formula a little bit more. If the sum is 325, how many consecutive natural numbers are added? What are we being asked for here? Well, we're given a sum of 325. We want to know what n is. So we have the equation 325 equals 1/2 n times n plus 1. Let's solve that. Now this is a quadratic equation. And I'm going to use the zero product principle. So we're going to follow the steps that Steve took us through in the last part of the lesson. I'm going to expand the right-hand side. That gives me 1/2 n squared plus 1/2 n. I'm also going to subtract 325 from both sides because I want to be able to factor the right side to apply the zero product principle. Now when I look at the right-hand side and I think about factoring, I'm not too pleased because I have fractions floating around. But you know, I can take care of that by multiplying both sides of this equation by 2. When I do that, I will clear the fractions from the right. And what I have is 0 equals n squared plus n minus 650. So now I need to ask, are there integer factors of negative 650 that add to 1? Well, 650 has a lot of factors. And I think what I'm going to do is the trick that Steve showed you and think about the prime factorization of 650. So I know 5 goes into 650 evenly, so that leaves behind, let's see, 130. 130 is divisible by 13 and 10, so I can write this as 5 times 10 times 13. 13 is prime, and 10 is 2 times 5. So I see that 650 can be factored into 2 factors of 5, that's 25, and 2 times 13, that's 26. And hey, 25 and 26, they only differ by 1. So it is the case that negative 25 and positive 26 multiplied to negative 650, and negative 25 plus 26 is 1. So let's factor. Going back to my quadratic equation, that factors into n plus 26 and minus 25 equals 0. So I get 2 solutions. Either n plus 26 equals 0, or n equals negative 26, or n minus 25 equals 0, which tells us that n equals 25. Okay, we're going to need to check. But let's think back to the context of the problem. N represents a natural number, so I'm just going to check the solution n equals 25. So what I'm going to do is use my formula for the sum of the first n consecutive integers. And I'm going to evaluate this for n equals 25. I want to get 325. That's what the problem was asking for. So if n equals 25, then 1/2 n times n plus 1 is 1/2 times 25 times 26. 1/2 of 26 is 13. 13 times 25, well, let's see. 10 times 25 is 250. 3 more 25s, that's 75. 250 plus 75, that's 325. That's what I wanted. So the sum of the first 25 natural numbers is 325. Here's another problem. An industrial engineer is designing rectangular platforms that are 3 meters longer than they are wide. If each platform needs to be 54 square meters, how wide should each platform be? With a problem like this, it really helps us to draw a figure. We have rectangular platforms. We're being asked for the width of the platform. So I'm going to let W represent the width of the platform. And here we're measuring our lengths in meters. We were told that the platform's length is 3 meters longer than its width. So W plus 3 is going to represent the length of the platform. So now what we need is we need to write an equation and then determine a solution to the problem. Well, we were also given the bit of information that these platforms have to be 54 square meters. Well, let's calculate the area of that platform and set it equal to 54. So the area is going to be the width times the length, and that has to equal 54 square meters. So let's solve this. Expanding the left side and subtracting 54 from both sides because I know I want to have one side of my equation equal to 0, I now have a quadratic equation that I can solve by factoring. Here it will be a little bit easier to find the factors that we want. We're looking for integer factors of negative 54 that add to 3. Well, 9 and negative 6 will do the trick. So I have w plus 9 times w minus 6 equals 0. Just doing a quick check of my factorization, things look good. So I have two possible solutions to the quadratic equation, w equals negative 9 or w equals 6. But in the context of this problem, w represents the width of our platform. Can't be negative 9, so w equals 6 is the solution I want to check. I'm going to check this in the context of the problem. So if the width of the platform is 6 meters, its length is 9 meters, because it's 3 meters longer than it is wide, and its area is just the length times width, which is 9 times 6, that's 54 square meters. And in fact, in the process of kind of checking my work, I have a pretty good conclusion to my problem. Another example. A rectangular garden is 10 meters by 15 meters. A border of uniform width is to be constructed along both short sides and one of the long sides. If enough concrete is available to cover 100 square meters, how wide can the border be? Once again, I'm going to draw a figure. So we know that our garden is 10 meters by 15 meters. And what we're doing is we're constructing a walkway of uniform width around 3 of the sides, the 2 short sides and 1 of the long sides. And the question is, how wide can the border be to use enough concrete to cover 100 square meters? So I want to determine the unknown and write an equation. Well, the unknown is the width of the platform, and I'm going to call that W. So I'm going to let W represent the width of the border. And I think I just called my border a platform. I was thinking of the last problem. And I'm measuring width in this case in meters, just like in the last problem. Now I want to write an equation. So I need to think about what the area of this walkway is. Well, I'm going to break it up into bits. I have 2 bits that are really the same size, that are 10 meters long by W meters wide. In breaking this up, I've got these 2 short sides, and I have 1 long side. So let's figure out what the area of each of these bits are. Well, the side bits are going to be 10 times W square meters. So I've got 2 of those. Now let's look at the long part of our walkway. Well, the length is going to be 15 meters plus 2W. The width is W. So the area of our walkway is going to be 10W plus 10W plus W times 15 plus 2W. And when I add that all up, that should equal 100 square meters. So here's the quadratic equation that I'm going to solve. So I had 2 of those 10W square meter bits plus the long part of the walkway, which is W times 15 plus 2W. That equals 100 square meters. I'm going to start by expanding the left side. 20W plus 15W plus 2W squared equals 100. And I'm going to move all my terms over to the left side and combine like terms at the same time. So I have 2W squared plus 35W minus 100 equals 0. Here's the quadratic equation I'm going to solve to answer this question. Now I notice that the 3 terms share no common factors. So I'm going to be looking for integer factors of negative 200 that add to 35. I'm just going to write down all the pairs until I find something. Hopefully I'll find it quickly. So let's see. -1, +200. I know that's not going to work. -2 and 100. That's not going to work. 3 doesn't divide in evenly. 4 does. That's not going to work. Let's see, 5 goes in evenly. -5, let's see, 5 goes in 40 times. There we go. That's what I want. Now I'm going to factor by grouping. So I have 2w squared plus 40w minus 5w minus 100 equals 0. Factoring by grouping, the first two terms share a common factor of 2w. Factoring that out leaves behind w plus 20. Factoring out the factor of -5 from the last two terms leaves behind w plus 20. I have a common binomial factor of w plus 20, leaving behind the binomial factor 2w minus 5. I get two solutions. Either w plus 20 equals 0, or w equals -20, or 2w minus 5 equals 0. Well, solving that equation for w gives me w equals 5/2. And I'm going to write that as 2.5 because I'm thinking about the width of my walkway. W equals -20 doesn't make sense in the context of this problem. So I'm going to check W equals 2.5 meters. So when I do my check, I'm just going to make sure that these 3 bits of walkway, when I add up their areas using W equals 2.5 meters, that I'm going to get 100 square meters. So if W equals 2.5, then the area of the walkway is, so I'm going to start with my 2 vertical bits in my picture. So I've got 2 times the width times the length, so 2 10 meters times 2.5 meters. And then I have 1 of the long horizontal bit of my walkway, that's 2.5 meters, by 15 plus 5 meters, or 20 meters. So let's see what I get. 10 times 2.5, that's 25. 25 times 2 is 50. 2.5 times 20, that's also 50. So 50 square meters plus 50 square meters, that equals 100 square meters. So the walkway can be 2.5 meters wide to use up the available concrete. One last example. The quantity of bell peppers sold at the local produce market depends on the selling price of peppers. The market sells 160 minus 2p pounds of peppers at a price of p-cents per pound. If the market had pepper revenues of $32 last week, how much did the market charge for a pound of bell peppers? So the thing we're going to use in this problem, the idea we're going to use, is that revenue equals unit cost times the quantity sold. Let's look at how we're going to use that. So we have this bit of information that's been given to us, that the amount sold in pounds is given by this expression 160 minus 2p, where p is the unit cost in cents per pound. So let's think a little bit about this. What's going on with the amount? The amount depends on the price. And if we look at this expression for the amount of pepper sold, we can see that it decreases as the unit price of peppers goes up. So in some situations, the amount sold can depend on the price of the item. That's what we have here. Now what we've been asked to do is to write a formula for the revenue, or we need to write a formula for the revenue to figure out what the selling price of the peppers were when the market made a revenue of $32. So let's do that. So revenue is unit cost times the quantity sold. So in this situation, the formula we're going to use for revenue is going to be the unit cost, p cents per pound, times 160 minus 2p pounds. Let's think a little bit about the units here. So the units on this expression for revenue, are they dollars? Are they cents? What do we have? Well, the units of p are cents per pound. And the units of 160 minus 2p, we were told, were pounds. Multiplying cents per pound by pounds gives us cents. So this is a formula that's giving us the market's revenue in cents. Now, what was the question? The question is, the market had revenues of $32. How much did the market charge for a pound of bell peppers? What was P? Well, first thing we have to think about is how many cents is $32? Well, it's 3,200 cents. That's where we're going to have to set our expression for the revenue equal. So let's do that. So the equation we're going to be solving here is our revenue expression needs to equal 3,200 cents. Let's get a quadratic equation that we can solve. So expanding the left side, in this case, I'm going to add 2p squared to both sides and subtract 160p, and that will leave me 2p squared minus 160p plus 3,200 equals 0. This is the equation I'm going to solve to answer the question. So 2p squared minus 160p plus 3,200 equals 0. Fortunately, all three terms on the left side have even coefficients, so I'm going to start by factoring out a 2. And now, factoring that trinomial, one of the things I noticed is that 1,600 is a perfect square, and in fact, when I factored out that 2, that made me kind of happy. 1,600 is 40 squared, and 80 is twice 40. I have a perfect square trinomial, which factors into p minus 40 quantity squared. So there's just one solution to this quadratic equation. The solution is p equals 40. But I want to check, and I want to check in the context of the problem. So in this case, the unit price of peppers is 40 cents per pound. Let's calculate the amount they will sell using our formula. So if P equals 40, then 160 minus 2P equals 160 minus 2 times 40, that's 80, which is 80. So this means that the market sold 80 pounds of peppers. What were their revenues? Well, the revenues is going to be the quantity sold times the unit price. So the market's revenue is 80 pounds times 40 cents per pound, which is indeed 3,200 cents. So now we can state a conclusion. The market sold peppers for 40 cents per pound to make a revenue of $32 on their pepper sales. So that ends lesson 12.